All right, good morning. So this is being recorded on March the 23rd, and like all of you, I'm sure we're in the midst of the coronavirus, so I hope you're safe and are staying that way, and staying isolated and socially distant. If you've got plenty of time to work on that, gives you some great time to look at your DE work. So today we want to begin to model in real world applications uses for our differential equations that we solved. And I'll tell you, we looked last time at a variety of ways to solve those, and there's still a variety of ways to solve those. And I tell you that because sometimes on the homework or the solution set, I may solve things as a separable equation. My students tend to like solving things as a linear differential equation. So any of that's fine. And if you pursue it one way rather than what I've done, ask me, and that's no problem. I'll be glad to go back and solve it for you with an alternate solution. The answer is the answer, right, regardless of our method. So today we want to think about what's known as compartmental analysis. That's a fancy way to talk about some mixture problems. So typically today we've got problems where maybe some water is entering a tank and maybe some water is leaving a tank at the same time, and we want to begin to model maybe what's going on with the chemicals or what have you in that tank. All of our problems today can be modeled using this kind of idea. So I'm going to talk about the chemical, and normally today anyway it's going to be salt. Let me use a lowercase. So I want to be able to model the amount of salt or whatever chemical I'm looking at any time t, right? And so again, we've got things entering a tank, coming in, and things leaving a tank. So I want to model both of those ideas, the in and the out, and the difference between those describes the amount of salt at any time t. Keep in mind, my units need to work themselves out here, right? So, salt is typically going to be measured in grams or kilograms or something of that nature, and then this is a time unit. So my tank has an amount of liquid in it. We need the units to work themselves out, okay? So to that end, let's look at number one, which I've already started. A 100-liter tank has pure water flowing into it at a rate of 10 liters per minute. The contents of the tank are kept thoroughly mixed, and that's just going to be so that the distribution is uniform and I can model it. It'll say that every time, but other than giving me the right to set my equation up like I'm doing, that's the only significance of it. Excuse me. And the contents also flow out at a rate of 10 liters per minute. So no salt's going in, but I've got some salt in the tank where some salt is going out. So I'm going to let S represent the amount of salt at any time t. And again, I want to set up both the in and the out. So let's do that. So the salt going in. So water is flowing in at a rate of 10 liters per minute. And there is a 100-liter tank, but there's no salt coming in. So 0 kilograms of salt. So my in rate is 0 kilograms per 1 minute, which essentially is 0. But what I want you to see is that my liters went away, and so I'm left with appropriate units for dsdt, kilograms per unit of time, kilograms per minute. That happens to be 0. The out rate, I've got some salt in the tank, I just don't know how much. Some salt's in the tank, right? S kilograms of salt are in 100 liters, and it's flowing out at the same rate, 10 liters per minute. All right, I reverse those fractions. It's commutative, so it doesn't matter. Don't let that throw you off. So I've got 10S per 100 kilograms per minute. Or better yet, S over 10 kilograms per minute is the out rate. So for this particular equation, ds dt is equal to 0 minus S over 10. And I'm going to omit the units there, but keep in mind it's kilograms per unit of time, kilograms per minute, kilograms per minute. So really the differential equation that I want to solve is a negative S over 10. So again, there's a variety of ways to do that. I think the easiest way maybe is to make it separable. So let's see if I multiply both sides by 1 over S, and if I multiply both sides by dt, then I'm left with ds over S is equal to a negative 1/10 dt. So again, it's pretty nicely separated. So I can now integrate both sides. ds over S, that's going to integrate into a natural log. And a negative 1/10 with respect to time is a negative 1/10 t plus some constant of integration. As happened before, I got a constant on the left-hand side as well. A constant and another constant is still a constant somewhere. All right, so to solve that, what I'm going to do is to exponentiate both sides. We've pulled that trick in the past. So e and natural log, those two things cancel each other out. And so I have e to the negative 1/10 t plus c. And if I make use of my properties of exponents, that's the same thing as e to the negative 1/10 t times e to the c. And e to the c is simply a constant. So that constant I've just put here in front, and then e to that power. So that's the differential equation that I actually want to work with. So this says the salt at any time t is equal to some constant times e to that power. So let's see if we can make use of some initial conditions. So back in my problem, it says initially the tank contained 10 grams of salt. It was already in the tank at time equal to 0. It's not flowing in. Pure water was flowing in. So I know that there's 10 grams of salt whenever t is 0. That says negative 1/10. Negative 1/10 times 0 is 0. E to the 0 is just 1. So it looks like C is 10. So it looks like my equation, or my model for this case, is S of t is equal to 10 e to the negative 1/10 t power. So that describes the amount of salt at any time t. In particular, we're interested in the amount of salt after or at 30 minutes. So ultimately, I want to find S at 30. So S at 30 is equal to 10 e to the negative 1 over 10 times 30 power. And I'll let my calculator, of course, do all that arithmetic for me. So 10 e to the negative 1/10, I'm going to put that in as a decimal, times 30. Looks like after S of 30, there is 0.498 kilograms of salt. Okay. Sometimes it says how much salt, if I had a secondary question, how much salt after a long time, which is not very mathematical at all, is it? But we can interpret that, how much salt after a long time, I can interpret that as the limit as t goes to infinity. of that function. And my function is this. So think about that with me for a moment. You've got fresh water entering the tank, no new salt is coming in, and water's leaving the tank. So as time goes on, that amount of salt should ultimately, it may not always disappear altogether. In fact, it'll just get infinitely small mathematically, but it begins to approach just a tank full of pure water. And let's just establish that by using this limit. So if I take this negative exponent, make use of that negative exponent and send that to the denominator, I have this function. So as t gets large, this exponent is getting large, and e to bigger and bigger numbers is getting bigger and bigger. But 10 divided by bigger and bigger numbers actually is approaching 0. So I begin to have no salt in the tank after a long time. That's not totally true because I can't measure an infinite amount of time, right? But it begins to decrease and get so small that you can taste the water and it doesn't taste salty at all. All right, look with me at number 2. All right, so take a moment and read number 2. A tank contains 1,000 liters of brine with 15 kilograms of dissolved salt. Brine that contains, sorry for my issue with the camera, brine that contains 0.05 kilograms of salt per liter of water enters the tank at a rate of 5 liters per minute. In addition, brine that contains 4.4 kilograms of salt per liter enters the tank at a rate of 10 liters per minute. The salt is kept thoroughly mixed and drains, is what that should say, drains from the tank at a rate of 15 liters per minute. How much salt is in the tank after t minutes and then after 1 hour? So this is a little bit different. So my in and out rate is still happening. But this is different in the sense that now I have salt coming into the tank, and actually I have it coming into the tank in 2 different ways, right? Two pipes of brine are going into the tank. So let's describe the N rate. So the N rate here is brine that contains 0.05 kilograms per liter is entering at a rate of 5 liters per minute. And in addition to that, there's a second N that says salt is coming at 0.04 kilograms per liter at a rate of 10 liters per minute. So when I cancel all of those units, the only units that I should have left should describe salt per unit of time, and kilograms per minute, so that's working itself out. All right, the out rate it says the solution is kept thoroughly mixed and drains from the tank at 15 liters per minute. So I have some salt in the tank. That's what we're trying to describe. S kilograms per 1,000 liters. And it's draining at a rate of 15 liters per minute. So I'm left with 15S over 1,000 kilograms per minute. And that, I'm sure, reduces, let's just do a decimal, I guess. So 15 1,000ths. S is the out rate. The N rate again is going to be 5 times 0.05. Plus 0.04 times 10. All of that is kilograms per minute. All right, so it looks like that the N rate is it's coming in at a rate of 0.65 kilograms per minute and going out at a rate of 0.015 S. So the change in salt with respect to time is 0.65 minus 0.015 S. That's the differential equation that I want to solve. And just glancing at that, it kind of sort of looks like, gosh, what might be the easiest thing? Maybe a linear equation in this instance. So maybe I'll move this S portion back to the other side. So here's the equation that I ultimately want to solve. And so that does fit the form of a linear equation. This is an S prime and an S term. So I'm going to use this piece and build my integrating factor. And I'm integrating t's at this point. Oh, I don't know why I put the t there, sorry. I am integrating t's, but I don't have one here. I'm integrating it. So that integrates into e to the 0.015 t power. So remember how that integrating factor works. I'm going to multiply this entire equation through by that, but the left-hand side is something that I can differentiate with respect to t. So again, I'm multiplying this term through the entire equation, so it ends up on the other side. All right, and I can now integrate. So integrate a derivative, we just get back this piece. Keep in mind, I'm ultimately trying to model S, right? I'm trying to model salt in the tank, so I need to solve for S. And then on the side, I need to do this integration. So if let me pull that constant out in front. So if I choose U to be 0.015t, then the du is 0.015. So I need to put one in and divide it on the other side. Looks like 43.33. Plus some constant of integration. All right, so if I divide this to both sides, another color. All right, so it cancels out on the left. On the right, this first term, it cancels out. And on the end, I'm just going to slide it back up into the numerator. Okay. All right, so let's see if we can use an initial condition. We're almost there. An initial condition, it says a tank contains 1,000 liters of brine with 15 kilograms of dissolved salt. So at time equal to 0, there's 15 kilograms. So I know 15 kilograms when t is 0. So it looks like C is going to be negative 28.33. So my model looks like S of t is equal to, you can swap these places if you feel like you need to. So there's just a model for the salt at any time t. And that answers the first question, how much salt is left after t minutes. This describes that. After 1 hour, we want to evaluate S at 60. And so I'll just plug that value in. So 43.33 minus 28.33 E to the negative 0.015 times 60 minutes. And I'm getting 31.81 for that solution. So those are nice problems. Those are some nice mixture of problems. I'm going to post a blank copy of those to look at. I'm going to post a blank copy of some homework for you to look at. And then I've got some solutions to that homework. And again, step through those. I may solve it differently than you want to solve it, and that's fine. It's just a different approach, but we should get the same answer. A lot of my students just tend to gravitate toward a linear approach, which is fine. I tend to see separable before I see linear, but we're getting to the same place. So I look forward to talking with you about those problems, and work on that for me this week. I'm going to post some growth and decay problems as well, and they're relatively simple.